Welcome everyone. In this video, I will talk about the properties of eigenvalues and eigenvectors. Let's start. For all these properties that I have listed, I am assuming that A is the matrix, a square matrix, and if lambda is its eigenvalue, then its corresponding eigenvector is x. So basically, I am assuming that Ax is equal to lambda x. So let us look at the first property. Any square matrix A and its transpose, some people also write the transpose like this, have the same eigenvalue. So for example, if I take a square matrix 1, 4, 3, 2, this is a 2 cross 2 example, and if you find its eigenvalue will be minus 2 and 5. And I ask you to verify, just don't believe that what I am saying. You can do this as a practice problem, that find its eigenvalue and then take the transpose of A. Transpose of A will be the matrix 1, 4, 3 and 2, and if you calculate its eigenvalue, the eigenvalue of the transpose will also be minus 2 comma 5. So by taking the transpose of a matrix, its eigenvalue does not change. Second property is very important, and it tells you that the eigenvalue of the triangular matrices are just the diagonal element. And when I am talking about these triangular matrices, I am talking about both upper triangular as well as lower triangular. I hope you know that what is an upper triangular matrix and what is a lower triangular matrix. So for both kind of such matrices, the eigenvalues are nothing but just the diagonal elements. So for example, if I take a triangular matrix 2, 0, 0, 3, suppose I write 4, 0, 7, 3 and 2. So what kind of the matrix is this? This is a lower triangular matrix. Why it is a lower triangular matrix? Because everything above the main diagonal is equal to 0. And since it is a lower triangular matrix, the diagonal elements are 2, 4 and 2. So the eigenvalues of this matrix, if I call this matrix A, is nothing but 2, 4 and 2, right? If I take another example, suppose I draw the example of a lower triangular matrix. Suppose I write 1, 7, 3, 0, 6, 5 and 0, 0, 2. Now this is an upper triangular matrix, right? Because everything below the main diagonal is 0. I hope you understand. This was a lower triangular matrix and this is an upper triangular matrix. So what are the diagonal elements here? The diagonal elements are 1, 6 and 2. So what are the eigenvalues? The eigenvalues are also 1, 6 and 2. So when the matrix is a triangular matrix, either upper or lower, we there is no need to separately calculate the eigenvalues. You just look at the diagonal elements, and whatever be the diagonal element, that element will be its eigenvalue. Yes. Now the third property is that if we have a matrix A and its eigenvalue is alpha, then if I take a matrix, or if I say its eigenvalue is because I have taken alpha already here, so I am calling something else. Suppose I say that we have an eigenvalue like lambda 1, right? Or lambda, just lambda. So if A has the eigenvalue lambda, then alpha times A will have the eigenvalue alpha times the lambda. Let us understand it through this example. So for the matrix 1, 4, 3, 2, I take this 2 cross 2 example. So the eigenvalues are here minus 2 and 5. You can verify this, that its eigenvalue will be minus 2 and 5. Now suppose I multiply this matrix by a scalar. Suppose that a scalar alpha I am taking is 2. So I am multiplying this matrix by 2. So I get 2 times 1, 4, 3, 2. So what will be the matrix? The matrix will be 2, 8, 6 and 4. Right? I have multiplied all the element by the number 2 or the scalar 2. Now this matrix was A. This matrix is 2A. So I am expecting, what is the rule suggesting? The rule is suggesting that the eigenvalues of this matrix should be 2 times minus 2, means it should be minus 4 and 10. because the original matrix was having the eigenvalue minus 2 and 5. So if you are multiplying it by 2, the new matrix would have this eigenvalue 2 times this minus 2 and 2 times this 5, that is equal to 10. So this is my claim. Let us verify that it is true or not. So to find the eigenvalue, first of all I am writing the characteristic equation, and I hope you know how to write the characteristic equation. That is lambda square minus trace of the matrix. So trace is 2 plus 4 is equal to 6. So that is 6 times lambda. And then we calculate the determinant of it. So what is the determinant? The determinant is 2 into 4 minus 6 into 8. So it is 8 minus 48, that is equal to minus 40. So lambda square minus trace of a times lambda and plus determinant of a. So determinant here is minus 40 is equal to 0. I have discussed in detail that how to write the characteristic equation in my previous video. So in case if you have doubt, you should watch that. Now this is the characteristic equation for this matrix. So if I take this characteristic equation and factorize it, I will get lambda square minus 10 lambda plus 4 lambda minus 40 is equal to 0. So if you take lambda common, you will get lambda minus 10, and if you take 4 common, you will get lambda minus 10. So you can clearly see that from this the roots will be lambda is equal to 10 and lambda is equal to minus 4. So the original matrix was having the eigenvalue, that is minus 2 and 5. If you multiply it by 2, the eigenvalues are also multiplied by 2. So this minus 2 becomes minus 4, which is this, and this 5 becomes 10. So we have got minus 4 and 10. So this is a very simple thing. If I suppose say that there is a matrix A and its eigenvalues are lambda 1, lambda 2, lambda 3, and if I ask you what is the eigenvalue of 7A, so it will be 7 lambda 1, 7 lambda 2 and 7 lambda 3. As simple as that, no confusion. Moving ahead, the fourth property is also very interesting, that a minus ki has the eigenvalue lambda minus k for any scalar k, and the corresponding eigenvector remains same. It means what? That I take the same example again. I take the example of this matrix, that is 1 4 3 2, and its eigenvalues are minus 2 comma 5. Right. Now if I define another matrix like this matrix, suppose I call as A. So if I define a matrix like A minus 2i, so here this k term I am taking 2. So this matrix will be what? This matrix will be 1 minus 2, that is minus 1, 4, then 4 minus 0, 4, 3 will remain same, and 2 minus 2 will become 0. I hope you understand that if I am subtracting 2i, I just have to subtract 2 from the main diagonal. All other entries will remain same. So my claim is that eigenvalues of this should be what? As per the property, the eigenvalue should be lambda minus k. So if original matrix has the eigenvalue minus 2 minus k, what is k I am taking? K also I am taking 2. So it should be minus 2, that is minus 4, and it should be 5 minus 2, that is equal to 3. So the claim is that eigenvalue of this matrix should be minus 4 and 3. You can verify that also. So to verify, you would need to write the characteristic equation, that is lambda square minus trace. So trace here is minus 1. So minus lambda means trace square plus lambda. And what is the determinant? This minus this. So 0 minus 12 is minus 12. So determinant is minus 12, that is equal to 0. And if you factorize this, you will get lambda square plus 4 lambda minus 3 lambda minus 12 is equal to 0. So you can take lambda common and you will get lambda plus 4. You can take minus 3 common, you can get lambda plus 4. So you can clearly see that the eigenvalues are minus 4 and 3, which is what I was expecting, that if eigenvalue is original matrix has eigenvalue minus 2 and 5, then A minus 2y will have eigenvalue minus 2 and 5 minus 2. Right. So it is very obvious. Suppose I take for example A as a matrix of size 3 cross 3, and its eigenvalues are lambda 1 comma lambda 2 comma lambda 3, and if I ask you what is the eigenvalue of A minus 3i, so the eigenvalues of A minus 3i matrix will be lambda 1 minus 3, lambda 2 minus 3 and lambda 3 minus 3. So this is how we can calculate the eigenvalue of a matrix. Okay, so let's move ahead. Now let's talk about these two properties which are very important. The sum of eigenvalues of a matrix is the sum of the elements of the principal diagonal, which is also called the trace of the matrix. So again I take a 2 cross 2 example. I am taking 2 cross 2 example. It is true for all kind of a square matrix. So don't be worried about what if the matrix is of bigger size. I am taking 2 cross 2 so that the things remain simple. So ladies and gentlemen, the eigenvalues of this matrix are given by -2, 5. You can verify this, right? I am making this claim. How to find the eigenvalue you already know. If you don't know, as I already suggested you, watch the previous video. So -2, 5. Now first thing that I am verifying is what is the sum of eigenvalue. So sum of the eigenvalue is -2 plus 5, that is equal to 3. And if I take the trace of the matrix, what is the trace? Sum of the elements along the principal diagonal, that is 1 plus 2, that is also equal to 3. So both are same. So this is the property number 5. What is the property number 6? So if you take the product of the eigenvalue, product is equal to, eigenvalues are -2 and 5, so -2 into 5, so it is equal to -10. And what is the determinant of this matrix? So if you call this matrix A, and if I calculate the determinant of A, this is 1 into 2 minus 3 into 4. So you can clearly see that this is 2 minus 12, that is equal to -10. So the product of the eigenvalue will be equal to the determinant of the matrix. So these two properties are very important. All properties are important, but these are especially more important. Now if you look at the property number 7, it suggests you that the eigenvalues of an idempotent matrix. What do you mean by an idempotent matrix? A matrix is said to be idempotent if A square is equal to A. So the eigenvalues of an idempotent matrix are either 0 or unity. To prove this, we can just consider this. Let me give you some explanation that what does it basically mean. Suppose I take a matrix A and I am saying its eigenvalue is lambda, means A times x is equal to lambda times x, right? Now if I am saying that A is an idempotent matrix, so I hope you will allow me if I multiply both sides by left, in both sides if I multiply A in the left. So A into Ax is equal to lambda into Ax. Here lambda is a scalar, so it can be written before the matrix. So next what I can see that A square x is equal to lambda, and for this Ax I can write lambda x because Ax and lambda x are equal. So this will become lambda into lambda x, right? Now this A square x, because A square is equal to A is an idempotent matrix, so it will become Ax is equal to lambda square x. Next I can rewrite it, lambda square x is equal to, and what is Ax? Ax is nothing but lambda x. So you see it is lambda x. So from this we get what? We get lambda square minus lambda x is equal to 0. And we know that x is a non-zero vector. It means lambda square minus lambda should be 0. So this gives me what? Lambda into lambda minus 1 is equal to 0. So from this we get lambda is either 0 or 1. So for any idempotent matrix, the eigenvalues will be either 0 or 1, right? This is a very interesting property. This one is also interesting, that if lambda is the eigenvalue of a matrix A, then 1 by lambda is the eigenvalue of A inverse. So for example, if I take the same matrix again, the 2 cross 2 matrix, 1, 4, 3, 2, and its eigenvalues are given by -2 and 5, right? These are the eigenvalues of this matrix, and this matrix is A. So what I am suggesting, and you need to verify it, this is something that you need to do. If you write A inverse and find its eigenvalues, so the A inverse will have eigenvalue 1 by -2 and 1 by 5, right or not? So it is a simple thing. Suppose there is a matrix A whose eigenvalues are 3, 7 and 5. Then what will be the eigenvalue of A inverse? The eigenvalues of A inverse will be 1 by 3, 1 by 7 and 1 by 5. So these are the this is the property number 8. Now move to the property number 9. Property number 9 is that A minus Ki inverse has the eigenvalue 1 by lambda minus k, and the corresponding eigenvector is x for any scalar k. So what it is suggesting, for example, if you have a matrix A, and suppose I say its eigenvalues are 3 and 5, I am taking a 2 cross 2 matrix, right? Now I am defining a matrix, or I am writing a matrix that let us write A minus 2i this is a matrix A minus 2i, and you take the inverse of it. So if I ask you what is the eigenvalue of this matrix, so as it is suggested here, what is the value of k? The value of k that I am taking is 2. So if the eigenvalues of A are 3 and 5, then eigenvalue of this matrix will be 1 by lambda. So if one of the eigenvalue is lambda is equal to 3, so I will take 1 by 3 minus 2, and another eigenvalue will be 1 by 5 minus 2. So eigenvalue of this matrix will be 1 by 1, that is 1, and 1 by 5 minus 3, that is equal to 5 minus 2, that is equal to 3. So this is how you can get the eigenvalue of A minus ki inverse. Yes or no? Suppose I ask you for the same, if what is the eigenvalue of A minus 8i inverse. So if I ask you eigenvalue of 8i in, see, this is not a new property. Basically this is just a combination of these two property. As I told you that if eigenvalue of a matrix A is lambda, right, then eigenvalue of A minus ki is lambda minus k. Now the eigenvalue of A minus ki is lambda minus k, so eigenvalue of A minus ki inverse should be equal to 1 by lambda minus k, as it is suggested by the property number 8. So property number 9 is basically a mix of property number 8 and property number 4. So I can write it. It is a combination of property number 4 and property number 8. If you use these two properties together, what you will get is property number 9. Okay. Now this is important. If lambda is an eigenvalue of an orthogonal matrix, a matrix is said to be orthogonal matrix if A inverse is equal to A transpose, right? The transpose I have written like A dash here. So it is suggesting that if A is an orthogonal matrix and one of its eigenvalue is lambda, then 1 by lambda will also be its eigenvalue. I repeat my argument. What I am saying, that if A is an orthogonal matrix, A is an orthogonal matrix and its eigenvalue, suppose I say, is equal to lambda, and I say that A is an orthogonal matrix, so lambda is an eigenvalue, so 1 by lambda will also be an eigenvalue. And this is also not a new property, it is a combination of the previous two property. Which two property? The property number 1, that any square matrix A and its transpose have the same eigenvalue, and then the property number 1 and property number 8. If you combine property number 1 and property number 8, you will get property number 10. I write it. It is property 1 and property 8. Property 1 is saying that eigenvalue of A and A transpose, eigenvalue of A and A transpose are same eigenvalue. And eigenvalue of if eigenvalue of A is lambda, eigenvalue of A inverse is 1 by lambda. Now you are saying that A and A transpose are, A inverse and A transpose are same, right? This is what you are saying, because this is the orthogonal matrix. So if I repeat my argument again so that you don't get confused. A is a matrix and it is an orthogonal matrix, so A transpose is equal to A inverse. This is the property. Second observation is that if A is a matrix and lambda is its eigenvalue, then what will be the eigenvalue of A transpose? The eigenvalue of A transpose will also be lambda, right? And what will be the eigenvalue of A inverse? Eigenvalue of A inverse will be 1 by lambda. Now you are saying that A transpose and A inverse are same, so 1 by lambda should also be the eigenvalue of A transpose, right? So this is what the argument is. So you keep this in mind. This property, the other property that I am going to talk about, the property number 11, it is also very important. Property number 8 is saying that if lambda 1, lambda 2 and lambda n are the eigenvalues of a matrix A. I am taking a general statement. If there are n eigenvalues, means this matrix must be of size n cross n. Then lambda 1 to the power m, lambda 2 to the power m, lambda n to the power m are the eigenvalues of A to the power m. Just to understand it through a smaller example, suppose I take the matrix 1, 4, 3, 2. I am taking this example again and again, and its eigenvalues are -2 and 5. And if I ask you what is the eigenvalue of A to the power 7, this is the matrix A. So eigenvalues of A to the power 7 will be -2 to the power 7, 5 to the power 7. If I take another example, suppose I take a matrix like 1, 0, 0, 0, 2, 1 and 2, 0, 3, and its eigenvalues are 1, 2 and 3. If I call this matrix B, and if I ask you what is the eigenvalues of B square, so eigenvalue of B square will be 1 square, 2a square and 3a square. So that will be 1, 4 and 9. So this is what this property is suggesting. Moving forward, let us discuss two more property. So the property number 12 is that for any real matrix A, when I say a real matrix A, means all its element in the matrix must be a real number, and if alpha plus I beta is an eigenvalue, then its conjugate alpha minus I beta is also an eigenvalue. And this is not a very special property, it is a very obvious property. Why it is obvious? That in your previous classes you must have studied that for any equation, if it has an imaginary imaginary roots always occur in pairs. So if alpha plus I beta is a root, then alpha minus I beta will also be a root, right? So if it is given that if alpha plus I beta is an eigenvalue, and what is the eigenvalue? Eigenvalue is nothing but the root of the characteristic equation. So if the characteristic equation has one of the root as alpha plus I beta, then certainly alpha minus I beta should also be a root. So if alpha plus I beta is an eigenvalue, so alpha plus I beta is an eigenvalue. So alpha minus I beta should also be an eigenvalue. And this is true for the real matrix only. In case if the matrix is complex, then this property will not hold. And lastly, the property number 13, that if lambda is an eigenvalue of a non-singular matrix. When I say a matrix is non-singular, means its determinant is not equal to 0. Then determinant of A time by lambda is the eigenvalue of the matrix adjoint of A. What is this property? I repeat, A is a matrix and its eigenvalue is lambda. Now what is the eigenvalue of adjoint of A? So eigenvalue of adjoint of A will be determinant of A by lambda, provided determinant of A is not equal to 0, because I am talking about a non-singular matrix. So these are some of the properties. I have listed them, I have explained them. What I would suggest you that you need to verify them one by one. You can also try to write a rigorous mathematical proof for it in case if you are interested. Otherwise, for your purpose, if you just remember the property and have understood it, that what this basically means, then it will be sufficient for you, right? So this is all in this video. In the next video I'll be talking about how to find the inverse using the Gauss-Jordan method, and then I will also talk about the Cayley-Hamilton theorem. I already have created a complete playlist, so in case if you have not been able to understand any of the topic, you should watch the previous videos. I have uploaded the video related to rank of a matrix, linear dependence, independence, system of equation, eigenvalues and eigenvectors. So thanks for watching. Do share with your friends and like the video as well. Have a nice day.